So here's the answer to your warm-up. Your warm-up question asks you to put these 4 items in order from the least amount of inertia to the greatest amount of inertia. Because more or less inertia is based off of an object having more or less mass, in this case, the object that has the least amount of inertia is the bullet. The bullet is the smallest thing, and that is why it can go fast. The next object that has the most inertia would be the 20-pound weights. The object with the third most amount of inertia would be the Olympic runner, and then the object with the most amount of inertia would be the car. Now, the most common mistake that people make here is that they think that the bullet has the most inertia because it goes fast. But the reason why it can go fast is because it has only a little bit of inertia. It is easy to make a bullet go really fast. But with a car, it is hard to make a car go really fast. You need a big engine to make a car go really fast. So because inertia is based off of mass, the bullet has the least amount of inertia, and the car has the most amount of inertia. What we're going to do today is I will just give you a quick, another example of inertia. So a couple years ago, my husband and I went to San Francisco, and everywhere you go in a big city like San Francisco, you have to take public transportation. And so we took the bus a lot of places, and on the bus, though, there's so many people that you have to stand up. So we had to hang on everywhere we went. Then we had to hang on to the rails. We had to hang on to a pole because while we're moving on a bus, and you've probably experienced this before, if the bus is moving, we are moving with the bus. Well, if the bus were to stop suddenly because we have inertia, we would want to fall forward because we were in motion and we wanted to stay in motion, so we had to hang on. The same thing was true, though, if we were stopped. Even if we were stopped, we still had to hang on in the bus, because if we were stopped and the bus took off, then we would feel like we were falling backwards. We weren't actually falling backwards, but we had to hang on so that we wouldn't stay in place while the bus moved. Because if we were at rest, our bodies would have wanted to stay at rest. We're going to move on today to talk about Newton's second law of motion. So would you please turn to IP 70, and we're going to take some notes. And the notes are going to be a little bit different because there's going to be some things you have to copy down and some things you just have to think about. Well, here's what you have to copy down. You have to copy down the title of your notes for today. We're going to move on to what Newton's second law of motion states. The first thing I want you to do is sketch this picture. There is a picture of a person, stick figure, pushing a shopping cart, and this person is pushing a shopping cart that has stuff in it. This one's empty, this one's full of groceries, so we would consider this to have a larger mass. Pause this video so that you can copy down this picture. Now, do not copy this down. I just want you to think and answer this question in your notes. Which one of these carts would take the most force in order to make it accelerate? Defend your answer in a complete sentence. When you're done with that, answer this question. Which cart would accelerate the fastest? Defend your answer in a complete sentence. Pause the video and answer these 2 questions based on this picture in your notes. Here's what you actually need to copy down. Copy this down. These are not your thoughts, these are Newton's ideas. Newton's second law of motion states that acceleration increases with increased force. Write that down and highlight it. So we're going to start by using these hand motions, and we're going to say that acceleration, we know that hand motion already, increases with increased force. Would you pause for just a moment and write down, what do you think that means? When you're done, take a look at this picture. Sketch this picture really quickly. You don't even have to draw the people. Maybe you just sketch these force vectors. Okay, so imagine we have a boy pushing an empty cart and an adult man pushing a cart. So both carts have the same mass, but in one case we have a smaller force, and in this case we have a larger force, in which case we would have greater acceleration because we have a larger force. So here's what this means. Newton's second law that says that acceleration increases with increased force, here's what it means. It goes faster when you push it harder. We have more acceleration on the cart when there is increased force. When there's more force, things go faster. But there's a second part to Newton's second law. Write this down. Right? But he also said that acceleration decreases with increased mass. Copy that down and highlight it. Now, think about those words. Acceleration decreases with increased mass. And just write a quick note about what you think that means. Here's another sketch. Maybe you don't need to sketch the boy and the cart, but maybe you sketch these force vectors. So let's say we have the boy putting a force on a small mass and a boy putting a force on a larger mass cart. The acceleration with the larger mass is smaller than the acceleration when you put the same amount of force on an object that has less mass. So here's what this means. It's really easy. Acceleration decreases with increased mass. Here's what it means. It goes slower when it's heavier. When there's more stuff in it, when there's more mass, an object will move slower. Acceleration will decrease. And this is the reason why we have the big guys. When we apply this idea to sports, we don't want the big guys being the running backs, right? We want the big guys being in the offensive line because they're not fast. They have more mass, and so their acceleration is less. Here's something else that you need to know about Newton's second law. Copy this down. There is a math formula that goes with Newton's second law. Newton figured out that you could calculate the force on an object if you knew the mass and you knew the acceleration. The math formula to calculate the force on an object is force equals mass times acceleration. And we can use the FMA triangle in the same way that we used it for DST. So copy down the FMA triangle. Another thing you need to write down is the units for each one. The unit for force we know is newtons with a capital N. Anytime you see a unit for mass, it would be kilograms or grams. And if you remember the unit for acceleration, it is meters per second squared. Write down the units for all of these factors. We're going to do one force problem together. Whenever you see a mass, we're going to draw a box around it. And when you see an acceleration, we're going to circle it, and then a force, we're going to put an arrow underneath it. Here's the first problem we're going to do together on your OP page. A bowling ball has a mass of 6 kilograms and leaves your hand with an acceleration of 60 meters per second squared. How much force did you apply? So Newton figured out that if you knew the mass of the object and the acceleration of the object, you could figure out how much force you'd have to apply in order to make it go that rate. So F equals ma, mass times acceleration. In this case, the mass was 6 kilograms times acceleration, which was 60 meters per second. 6 times 60, 6 times 6 is 12. Add the tens or make it hundreds, and the answer is 120. And since the unit for force is newtons, our answer is 120 newtons. So here's what I want you to do. I want you to reflect on your notes. I want you to work on OP to do the rest of the force problems. But I want to review Newton's entire second law. Newton's second law states that acceleration increases with increased force, which means it goes faster when you push it harder, but acceleration decreases with increased mass, which means that it goes slower if it has more mass. You have one cool down question. The cooldown question for today is, and it's not Wednesday, sorry for that typo. According to Newton's second law of motion, discuss the amount of force that it would take to make each one of these boxes accelerate at the same rate. If we wanted these boxes to both go the same rate, what kind of force would we have to put on box A versus box B? And here are three possible sentence frames that you can use in order to answer this question. When you're done with your cool down, go back to your OP page and finish your force problems.